is Shaunak Kashyap. I'm a developer at Elastic. Elastic is the company behind several open source projects, the main of which is Elasticsearch. I'm not a developer on the Elasticsearch team. I'm a developer on the Cabana team. If anyone's familiar with Cabana, they'll know that it uses Elasticsearch quite heavily under the hood. So I'm very familiar with Elasticsearch. So today's talk is an introductory talk to Elasticsearch, and it's more about the search side of Elasticsearch. Specifically, if you have an application, how would you add search, or like a search UI to it, powered by Elasticsearch? So I'm going to start at the very high level, just start for anyone who isn't familiar with Elasticsearch, just start with what it is and what it's good for, what you can do with it. Then we'll talk a little bit more about, we'll actually dive right into the code at this point and look at how to tie it into your application. And then finally, time permitting, I have a few slides on how, when your application makes requests to Elasticsearch, how does it process these requests under the hood? So probably the most common use case for Elasticsearch is just full text search. So this is a screenshot from Wikipedia where user puts in some keywords and it just searches Wikipedia for all the articles that, no worries, that contain those keywords and returns them. This is the most common use case for Elasticsearch. It's what Elasticsearch was built for when it was first started as a project about 6 years ago. And by the way, Wikipedia does actually use Elasticsearch under the hood. The next use case is similar to the full text one, except it's more structured. And that's why it's called structured search, where you're not just searching for keywords across all your documents in all their fields. You might be searching for keywords in specific fields. So this here is a screenshot from GitHub where I'm searching this repo, specifically pull requests in this repo that are open and by a certain author. And by the way, GitHub also uses Elasticsearch under the hood. So Elasticsearch can support these sort of very broad full text search requests, but also these sort of more structured requests. The next one, which kind of goes hand in hand with search results, is this notion of a faceted navigation. So typically we have, depending on your search, you could get back hundreds, thousands, millions, maybe even search results. And as we all know, we usually don't click past the first page or the second page maybe at most. And so it's important to give the user some sort of an aggregated view of these results, just so they can make sense of it all quickly. And that's where this faceted navigation on the left-hand side comes in. So this is a screenshot from Kayak. It does not run Elasticsearch, just for the record, although we wish it did. The results are shown on the right, and then they're aggregated on the left by various groupings, right? There's, in this case, there's all the arrival and departure times, and then there's airports below that you can't see, etc. So this is also another common place where this shows up is like Amazon on product searches and that sort of thing, right? Elasticsearch can power the aggregations that make up that faceted nav very, very fast as well. And the beauty of it is really it can generate this entire page with a single request. It can return the search results and the aggregations for those results all in a single response. And within, obviously depends on your search, but typically within tens of milliseconds. So it's not counting the network round trip, but in terms of generating the results itself, it's extremely fast. So, and if you're looking for if you want to go back and Google what to look for in Elasticsearch, that would be aggregations, the term you're looking for. Aggregations also powers this use case of analytics, which is, so what are aggregations? Let's just talk about that for a second, right? Aggregations take a list of results and put them in buckets. They're kind of like the group by clause in your SQL statement, right? And each bucket has certain properties. At the very least, every bucket can tell you how many documents are in that bucket. So it has this notion of a count, right? But let's say your document has a, what's a good one? So let's say it has a geo property, like a lat long in there. So it can also group things by like little bounding boxes, if you will, and return counts for those. And then you can take that and then put it on a map. So this aggregations capability in Elasticsearch is not just good for generating the faceted nav in a search results page, but also for if you have numeric data, especially for doing some sort of analytics. This over here is a screenshot from Cabana, which is the project I work on. This is an older screenshot. I mean, it's the most recent stable version of Cabana, but there's a newer one coming out in a few weeks. So, or a few months. I shouldn't overcommit. And screw my team in the process, right? Yeah, so anyway, this is Cabana. If you're not familiar with it, it's another open source project just like Elasticsearch, and it builds on top of Elasticsearch. So that's a little bit about what Elasticsearch can do. Let's talk a little bit about what it is, what its features are. It's like many NoSQL data stores. It is also document-oriented. It speaks JSON, JSON in, JSON out. Has a REST API for you can pretty much do 95% of the things you need to do via the REST API, including administrative calls and such. Obviously, some things require sudo, and you're not going to be able to do that through the REST API. It is schema-free, which is kind of fuzzy in that by default, you don't need to specify a schema for your documents when you index them. But if you want to, you can. And what we often see is people who start developing with Elasticsearch initially will not specify a schema because they don't necessarily know the schema for their data at the time. But by the time you get into production, you at least know partially what your data looks like, and you might want to add some validation, et cetera. So then you do specify a schema. It's distributed and it's clustered. So what I mean, and we'll see a little bit of this in detail later, but it not only distributes the data you give it amongst multiple nodes, but it also distributes the work done on that data, whether that work is indexing the data or searching for the data, et cetera. And of course, because it's distributed and it can scale horizontally, you can add more nodes and it will sort of rebalance the cluster automatically behind the scenes, et cetera. And it is clustered. What I mean by that is from an applications point of view, you can treat it as a single entity. You don't need to know that there are 7 nodes or 5 nodes at any given time. Every node, depending on the configuration, but by default, every node exposes the REST API that I mentioned earlier, and it doesn't matter which node you send a request to. It will internally figure out where that request should be routed. It will coordinate the responses internally and return a unified response back to you. So again, all of this is to say that you can treat all these nodes in the cluster as just one unit from an applications point of view, which is nice. So we're going to look at some code very soon on how to integrate your application with Elasticsearch. But before we can do that, we kind of need to be familiar with some of these very basic concepts in Elasticsearch. So the first one is a concept of a document. So I've already mentioned this. It's a document-oriented data store. Document in Elasticsearch is really the unit of data storage. Is kind of the best way to think about it. It's when you index a document, you are specifying it in JSON format. So an example would be, let's say an email. You want to store emails in Elasticsearch for searching. So you can imagine a JSON representation of an email which has fields like from and to and CC and body, etc. And that's your email document, and that's what a document is in Elasticsearch. An index then is just a collection of documents. So if each document represents an email, you might have an index called emails, plural, where you are indexing these documents into in Elasticsearch. Type is a dangerous notion, but I should mention it for completeness. Type is kind of a way to further subdivide an index. So going with the same emails example here, maybe you have an index called emails, but maybe you have 2 types within it. One messages and one called attachments. And in the messages type, maybe that's where you store these email message documents. And the attachments type, maybe you store these attachment documents that are maybe base64 encoded because they may be binary and whatever. So now you have an index with 2 types, and each type is receiving a certain, type of documents. That's great, except there is a little bit of danger using types. Types were introduced because of the use case I just spelled out. But over time, we realized that they actually cause more harm than help. You can run into issues where, I'll mention one of the issues you can run into, but there are several. For example, if you have a field in two types within the same index that is named the same, the field has the same name, but it has a different data type. Like in one type, it may be defined as a string, in another one as an int. Elasticsearch is not going to be happy. And earlier versions of Elasticsearch, not the current one, the earlier versions would actually happily accept them and just corrupt the index. Obviously, that's been fixed. Now, the newer versions, I believe the latest one, which is about to come out, will actually just like outright reject things and throw an error. So it's a lot safer. Having said all that, it is just better not to use types. So I mentioned them for completeness, and I also mentioned them because an index has to have at least one type. So what does it mean to not use types? Well, it just means that don't let your index have more than one type. So going back to our example of emails, just create two indices, one called email messages and one called email attachments. And that's the way you get around that. One thing, I think we have some time so I can get into this. Elasticsearch is built on top of Lucene. Lucene is a Java library that is pretty much the de facto library for information retrieval now in today's world. So Lucene does not have a concept of types internally. And it's a notion that was introduced by Elasticsearch on top of Lucene. So because Lucene doesn't have a notion of types, Elasticsearch has to sort of mangle the data and fit it or shove it into Lucene in a certain way. And that's sort of where all these problems started coming up. So there's been talk for at least a year of possibly just getting rid of this notion of types. It's not that easy. It's used a lot, unfortunately. And there are some use cases where you actually need to have types. So we'll have to figure out how to implement those use cases or support those use cases if we were to get rid of types. So they're not going away anytime soon. So if you're already using them, don't worry about it. But if you're not, don't use them because they're kind of dangerous, as I mentioned. So we have indexes, which are the overall collection. They're analogous to a database in a relational database. We have types, which are analogous to sort of tables, if you will. And then we have documents, which are analogous to rows. So if you think of it conceptually, you can think of it that way. And knowing these three, now we can pretty much start using Elasticsearch, which is what we're going to do next. So what I have here is a really simple application because that's how demos go. And it's a recipe search. By the way, there's a story here. The creator of Elasticsearch, his name is Cabana. He originally created Elasticsearch. This was, again, like 6 years ago, all by himself. He started out all by himself as a project because his wife was going to culinary school in London. And she didn't want one. I'm pretty sure she didn't ask for this, but he took it upon himself to create a recipe search engine for her. Because he was like, no, he was unemployed at the time, so he had, idle mind, whatever. And so she was going to culinary school, and she had all these recipes, and he noticed that her recipes were just a lot of unstructured data, essentially, and different types of data. And so he was like, all right, I will make this for you. And of course, he over-engineered it to the point where there is no recipe search today. Like, that still hasn't been delivered to his wife. But we have Elasticsearch, thanks to that. Anyway, so this is my poor man's attempt at a recipe search application using Elasticsearch. So this is what we're going to look at today, the code. What I'll do is kind of do this in two parts. First, I'll just walk through the app, just sort of like a live demo, so things may break. And then we will try to map the different parts of this application to actual code. And I'm not going to spend too much time on the code because, frankly, it's boring. But I will point out just the Elasticsearch parts of it, so you can kind of get an idea of how easy it is to build this application or an application like this. And by the way, the code, everything I'm going to show you here is on my GitHub repo. I'll share the slides on Twitter as well after the talk, so you can grab them and get it from there as well. Excuse me. All right, so this is where I switch windows and things usually break. Okay, so let's start by just getting a tour of the application itself. So it's a recipe search, right? So it's really simple. It starts out with a search, simple search UI. And let's say I'm hungry for things that contain beans. And as you can see, it returns responses pretty fast. Couple things I'll point out right away. Can everyone read this, by the way? Okay. Notice that the first two results contain bean in the title. Not beans, but bean, even though I searched for beans, and we'll talk about that in a second. The third one doesn't have beans anywhere over there. It was still returned. And so let me explain that first. Basically, what all that is there are other fields in recipes, like ingredients, which you're not seeing here in the results, but ingredients and directions as well. And the word beans probably appears in them, or bean appears in them. That's why you're seeing that. Of course, so that answers that question. The first question that I posed, which is, we searched for beans, but we got back the recipes that have the word bean in them. Why is that? So this is due to a process called analysis in Elasticsearch. So whenever you index a document, so in this case, a document represents a recipe. Whenever you index a document in Elasticsearch, it basically takes all the words in that document and normalizes them. One of the things it does as part of normalizing is stemming them down to their root forms. So plurals and singulars will all basically get stemmed down to just singulars. It might go further than that. Even words like jumped and jumping and jump may all get stemmed down to just jump. So as a result of that, when I indexed the first two documents, it saw bean and it indexed it as bean, that one word. When I search for beans, plural, it runs it through the same analysis process. It runs my search query through the same analysis process. So because of that, it normalized beans to bean as well, and then it becomes really easy to just compare these normalized versions, within Elasticsearch. And that's a very, very high-level introduction to analysis. There's a lot more that happens. There's different types of analyzers for different human languages. I'm using the English analyzer here because my content is in English, but for example, there's a German analyzer because German has a lot of compound words, and so it has different rules for how you might decompose them and stem them and etc. GitHub uses, pretty sure, has some sort of you can write custom analyzers too, and GitHub has one because it runs its code search on Elasticsearch. So that code is analyzed, it has its own syntax as well. So yeah, you can do all sorts of fun things there. So yeah, so this is the simple search UI. I also have an advanced search, which is, as you would expect, you can specify, individual fields and then combine them in some way and do a search. So if I search for bean in just the title, I should only get back 2 results now, which I do, because as we saw earlier, there was no bean in the third results title. And you can combine things. So maybe I only have I don't know why, but I only have 10 minutes to prepare, so I can restrict things that way, etc. Or that's not the one I would want. I would want that one. But yeah, and there's no recipes that have bean and take less than 10 minutes to prepare, so nothing came back. So that's the advanced search UI, and then finally, the third piece of this is just a way to add a recipe, and because I've obviously seeded this with some recipes, but you need a way to get data in as well. So that's what this UI will use. So that's just a really quick tour of the application itself. Now let's look at the code behind it. So we'll start with the code for this page, the simple search page, and I'll just run the search here. So I'm not going to go line by line. I'm just going to point out specific parts here. Is that readable in the back? Okay. So the key, I'm loading a bunch of JavaScript, which we'll look at. I should mention before we start, in this case, the architecture is really simple. I have a front-end application that's just HTML and JavaScript, and there is no back-end server other than like a Python static web server, but there's no Node.js or anything running in the back. So what that means is the client side, the browser, the code in the browser, is directly talking to Elasticsearch. I tried deliberately not to use any particular frameworks like Angular or React or whatever. Obviously, so I'm using oldish school jQuery. I don't think anybody does that anymore, but I figured it was kind of a nice least common denominator. So that's why I'm going with that. The other thing I'll mention is because the client is directly talking to Elasticsearch, this means Elasticsearch is exposed to the browser. Like it's, I can access it from the browser. You don't want to build your application that way, because then, if you can index and delete and whatever documents in it, anybody else can as well. So typically, you would have an intermediate layer on a server which talks to Elasticsearch, and then you would just expose parts of it or subset of the APIs to the client, or do some kind of proxying or something. But again, I wanted to keep this simple and just so we can go quickly. All right, so here, the main part of this is just this form, and it has a field called Q. So what happens is when you submit this form, that gets processed over here, and we'll get to that in a second. But first what we do is we need to create a client. This is like a connection to Elasticsearch, basically. And as I mentioned, I'm using jQuery, and that has an Elasticsearch plugin. But even if I wasn't using jQuery, I could directly just include the Elasticsearch.js library, and then I think the syntax is that. It exposes a global object called Elasticsearch, but it doesn't matter. You can get a handle on the Elasticsearch object and then just call .client on it to create a connection. This takes a lot of parameters. I believe all of them are optional. I spelled one of them out just for clarity here, and that's, well, where's the cluster? Where do you want me to connect to? As you can tell, hosts is plural, so it can take more than one. And that's because your cluster may have more than one node. And the reason for specifying more than one would be maybe the first one isn't available at the time or something like that. And so there's a fallback there. It really only connects to one node initially. And it does something called sniffing, where it will then ask that node, OK, tell me about all the other nodes in the cluster. And it gets back their addresses and stores them behind the scenes. The client does. That way, if in the future, if a request to one of the nodes fails, it can sort of quarantine that node and make the request to another node and all that kind of stuff. So the client handles all that for you behind the scenes. One of the reasons why you want to use an Elasticsearch client and not directly go against the REST API, because it has all these sort of smart features. And by the way, obviously this is all JavaScript, but there are clients in .NET, PHP. There's one in Perl for some reason. So yeah, you have options. OK, so we create a client. This is, as you can tell, a synchronous call, so it's going to block until the client's ready. And then we have this, we set up a handler for the form submission. And essentially what I'm doing here is grabbing the value from that field, the Q field in the form, and I'm running a client.search. So the client, the nice thing about the client, Elasticsearch client, is it's got a very flat API structure. Like everything just hangs off of the client object itself. So you don't have to, it's good and bad, right? In some ways it's good because it's easy to figure out what's going on. You can just inspect the client object, especially in JavaScript, and just like see what's available. It's very well documented as well. The bad, of course, is it's very low level. So that's kind of the trade-off there. But there is a method called search on it, which takes, and all the methods, by the way, take this sort of options object. And they all correspond to options on the REST API. So there's a one-to-one correspondence there, which is also kind of nice in some ways, because if you understand the REST API, you basically understand any of the language clients. Again, the downside being there's a one-to-one correspondence, so you're working at this very low level here. Certain languages, I think like the .NET client offers two versions. There's a low-level version, which kind of looks like this, and then there's a higher-level version, which lets you sort of pass in like native objects, and it'll do the right serialization, or serialization, etc. So in this case, all I'm saying is, well, call the search method. I want to search this particular index called recipes. I could have omitted the index parameter and I would have just searched every index on the Elasticsearch cluster. And sometimes you want that. I could have also, if I had, for whatever reason, multiple recipe indexes, I could have used wildcards, and that will work too. And then I specify the query parameter itself, that whatever it is that I type in here, basically. And that results in a bunch of results, and then I pass them to this show search results function, which I've defined separately because I'm going to use the same one in the advanced search as well. And that's what this looks like. This is just an HTTP response. It has a particular structure, so I have to kind of index into the hits to get the actual search results, and then I just render them. There's nothing really interesting over here from an Elasticsearch point of view. If you have questions, just stop me and ask. Otherwise, I'm just going to keep going. I think looking at code is pretty boring, so I'm trying to go through this section pretty fast. OK, so one thing I will do here, though, at this point is set a breakpoint so we can actually see this in action. That way, you're not just looking at static code in the website and trying to piece it together. And I won't go through the rest of the sections in as much detail, even because you've covered some of the main parts here. So let's start with, actually, I don't even need to do that. Let's because the browser is directly talking to Elasticsearch, we can just look at the network request. So exclude all that. And now if I search for beans, this is the actual request that the JavaScript client of Elasticsearch sent. OK, I should probably move this out to its own thing. So it's a little, yeah. This is the actual request that the JavaScript client for Elasticsearch sent to Elasticsearch. Remember, Elasticsearch exposes a REST API, so it's just an HTTP request at this point. The main thing to look for is it is a post request, but it has a query string parameter, okay, and that's just the value. The response looks kind of like that. Not great, so this is better. I won't again walk through this line by line, but I'll start at the bottom. Took is the number of milliseconds it took for Elasticsearch to generate this response on the cluster itself, not counting any round trip network time. So as you can tell, it's pretty fast. I don't have a lot of data, but it's still pretty fast, just 1 millisecond. Nothing timed out. There were a total of 3 hits in my results, and it has to rank order these hits somehow, right? Just like search results in Google are rank ordered. It just tells you what's the highest score of the hit that basically is at the top. Maybe that's valuable to you. And then there's the actual hits array itself that contains the results. Sorry. Each of them has these few metadata fields up top, index ID and this type down here. The ID is the ID of the document when it was stored in Elasticsearch. The index is the index, and the type is that bad thing that we talked about earlier. And the score is the score of this particular hit in the search results. And what you're interested in from like an application rendering point of view is this source field. And this is what actually contains the data that you indexed into Elasticsearch. So this has a bunch of things like the cook time and direction and description and whatnot. And I'm only showing the title and the description and I don't remember exactly what else, but title, description, preparation time, and cooking time. So I'm only showing 4 of these fields. It is possible, and I haven't done this, but it is possible to tell Elasticsearch, well, only return those 4 fields. I don't want you to give me all this other, don't be chatty, basically, on the network. So you can do that. It's pretty simple. Also, by default, the search API returns 20 responses. You can paginate through them, of course. And it will return them in order of this score. It determines, for whatever reason, it decides that this document that's expanded right now is more relevant than the next one for whatever search query you did. It has a pretty good algorithm under the hood to figure that out. But you can order them by something else. So you might want to initially maybe display them in this format, and let's say you wanted to then sort them in the UI by prep time or something. You could implement your sort only on the UI, but you could also just make the same request again with a sort parameter and pass in that field, and it would just resort them. So again, if you know the Elasticsearch REST API well, it maps pretty well to the client. So I would start with those docs and then go to the client docs. Anyway, so that's a little bit of detail, quite a bit of detail on actually what's happening under the hood from in the client side, that is. So let's quickly go through advanced search because it's not going to be that different. Oh, sorry, what am I doing? Yeah. Actually, that's not true. Advanced search is pretty different. So before we look at the code for advanced search, it's going to make a little more sense to look at the request that goes through to Elasticsearch. So yeah, okay. So let me kill that, and let's search for beans in advanced search. Just beans. That's the only field I've specified. And there's that options request because of course, but then here's the actual request that was advanced search request that was sent to Elasticsearch. And what I'm doing in the UI here is I want to do an AND between all these fields. So there's a query for that. There's a corresponding query for that in Elasticsearch. And it's called the bool query. So you can do ANDs, you can also do ORs, you can do NOT. And if you remember with ANDs and at least two of those, you can pretty much construct any logical expression. So the bool query looks something like this. It takes in up to 3 clauses, must, should, and I think it's called, might be just called not. I can't remember now, but I don't think it is. Anyway, there's a must, should, filter, right? That's the one, must, should, and filter. So, geez, I'm getting this wrong, I'm sorry. But anyway, there's a clause corresponding to and, or, and not, basically. Must is the clause that you want to use for expressing an and expression. So, and then that is an array of, all the things you want to AND together. So because I only specified one field, the title field, I want to express that the title should contain beans. So that's using this subquery called match. And this is the field name, title, and that's the value. So Elasticsearch supports many different types of queries. The match query is probably the most common one. That's how you say I want to match these words in this field. That's what I'm saying here. I want to match beans in the title field. There's another variant of it called match phrase, where you want to do phrase matching, not just individual words matching. There's regex. It's kind of, again, depending on the regex, it could be bad, the performance, but it is there. Then there's bool. Bool is also a type of query. Just like match is a type of query, bool is a type of query. The only difference is bool can take other queries as part of it because that's what it does. So that's all it is. That's what my compound search or advanced search query looks like. Now, obviously, if I say description contains, let's see, let's try to narrow this down. Burger, yeah. So now my new query will have 2 clauses under must, right? And they look very similar. So nothing great there. But let's try to add a non-text field. So let's say I want my prep time to be at least 10 minutes for whatever reason. Maybe I need to go take a shower or something. So, so now I go and I should have 3 clauses, which I do. And the first and the third one are those 2 from earlier. But now I'm using this third or new type of query called the range query, which is useful for specifying numeric range matches. So here I'm saying where the prep time is greater than or equal to 10. Prep time in minutes, that's what my field is named, is greater than or equal to 10, which is what I specified here. And the last thing I'll point out here is, let's say I add another, let's say I want it to be between 10 and 20 minutes. So obviously I should have, the way I have implemented this is I actually end up with 4 clauses. So the first and the fourth one are what we've seen before. And then I have 2 separate range queries here. One that says prep time is greater than or equal to 10, and another one that says prep time is less than or equal to 20. I could have combined these. The range query actually takes both. I could have made this into one line, so to speak, which would be prep time is greater than or equal to 10, comma, less than or equal to 20. I didn't do it because it was actually more of a hassle to construct the query that way in the client-side code, and it has the same effect. Under the hood, Elasticsearch is going to optimize your query anyways, so it doesn't really matter. All right, so now that we kind of understand the structure of the query, of the request that's being sent to Elasticsearch, we can see how it's constructed on the client side. And I'm not going to go through this in too much detail, but basically I grab all the elements from the form, and this is the part where I'm constructing the body. So you see the query, bool, and must. So that's what the query, bool, and must here are. And then obviously I have to construct the must clauses, which is what I have a bunch of, I send it through a map function. I filter out anything that's basically empty. And the map function, this is where the meat of the code looks something like this, where I say, well, all my fields that are strings, create a match clause for them. For all my for my fields that are integers, well, I still want to use a match clause, but I want to parse the field as an integer, that's all. And then for these two sort of range type fields, preparation time and cooking time, I use the low versions of those, and I construct the greater than equal to part of the range query, or the range query that has the greater than equal to. And then I do the same thing with the high versions, but this time I use less than equal. I'm doing a little bit of a hack here where because this weirdness that you see with the length -4 is a total hack, where the field in the form is this field, for example, and I'll just inspect it so you can kind of see what that is. It's called prep time min _ low. And the next one is called prep time min _ high, and so on. So, but the field in Elasticsearch is called just prep time min, right? Because I'm just storing the preparation time in minutes. The low and high are just the UI field that I need in the UI. So I'm basically just stripping out the low and the high. That's what I'm doing with this mess over here. There's going to be better ways to do this. Again, just want to make sure it's just easy to understand for the demo. Anyway, so basically it just passes every element through this function to get the right query for it, and then it combines all of those into this must clauses array and passes it, which is what you see, which is what you saw over here. So that's it. That's how advanced search works. The search results are identical. It actually just uses the same function. And so the last piece, from a code point of view, that I'll talk about is this one, which is actually creating a new document or indexing a new document in Elasticsearch. And this is also really quite simple. I think I call it add. So you still have your client. All of these, first create the client. So that part is the same. When I submit the add form, this guy over here, I basically just go through all the elements and add them to the body. And I basically create my JSON body representing a recipe. And I pass that into index. I have to tell it the index method on the client. I have to tell it which index and which type, and that's it. Obviously, I'm doing a little bit of, type conversion here. Again, all my string fields like title and just description I just pass them in as strings. But for anything that looks like minutes or numbers, like the minutes of cooking time, preparation time, and the number of servings, I just parse them as ints. So nothing fancy there either. The interesting parts, more interesting parts, are these ingredients and directions, which are arrays. There's a list of ingredients and there's an ordered list of directions. So, by the way, in the UI, I've hard-coded this to 3 and 5. You can do other UI things to make it expandable, whatever. It doesn't matter from a code point of view. So what I'm doing with ingredients here is I'm taking the array, which is an array of form elements, and I'm basically going over them, excluding any ones that are empty, and then I'm just extracting the value from each of them. That's all I'm doing. And so the result of this is going to be just an array of the actual values in these fields. That's all. There's nothing fancy going on here. And I play the same game with direction. So what I'm sending into Elasticsearch for these two fields is not a string, but an array of strings. And the nice thing is Elasticsearch actually doesn't care. Whether you send it a string or an array of strings, it's going to index them the same way. And that's because it actually doesn't even care if it's a string. It's going to break it up into tokens and run it through that analysis process anyway. So it doesn't matter if the tokens are, if there's 5 tokens or 5 words, for simplicity's sake, in one string, or if there's an array of 2 strings, one that has 3 words and one that has 2. At the end of the day, there's just going to be 5 tokens in Elasticsearch. So that's nice. Tags, again, nothing special going on here. All I do is, because I say you can specify them comma separated, I just split them on comma to create an array, trim them, and then I exclude anything that might be empty at the end. That's all. So again, tags ends up as an array of strings in Elasticsearch. So yeah, I'm not going to run through this because I don't want to type all this out, but you get the idea of how easy it is to just index something in Elasticsearch. And that's it for the demo part of it. Obviously, there's a couple things missing here, like I think I did implement like a view function or a view. So you can just see the recipe. So there is a GET request you can make in Elasticsearch to just get a individual specific document, not a search, but like here I know the document ID, go get it. And that's what's obviously powering this. I have not implemented delete and update because they're pretty boring once you know the other ones. You can do that on your own if you want. But yeah, that's it for the demo part of it. I know I went through that a little fast because I kind of want to get to this last section, which really tells you how some of these requests work under the hood in Elasticsearch. Before I jump in here, because I've gone a little fast, I'm going to drink some water. Does anyone have any questions?
Actually, I mean, maybe you'll get into this in the last section, so if that's the case, just go ahead. The last result you had didn't include the word bean at all, right? So is there like a NLP part of it or something, which, like it's a garbanzo bean in the hummus.
Yeah.
Which I thought was cool. How does that work?
Yeah, let me explain. I've run into a problem here where everything's locked. So I need to this happens before because of the HDMI. So I need to kind of, I think at this point I have to restart my computer, unfortunately.
Oh.
So I'm just going to kick that off, and then I can't even do that. Wow. Oh yeah, I don't need to restart. I'm sorry. I just need to run through the end of the presentation. Then it kind of unlocks me. Yeah, this has happened to me before. It's something to do with HDMI and my laptop. Sorry. I will answer your question though. Apologies. Okay. Let me just get back to where we were. I was trying to get back to the browser to bring up what you were referring to. That's kind of how I got myself in there. Anyway, so the question was that in the third result, there was no bean in the title or the description. But yet, when we searched for bean, it returned that result. So is there any natural language processing, I think was your question going on? No, there isn't. It's just that the word bean occurs in another field.
Oh.
That's all it is. It's you can say, and actually, should I risk this again? Didn't work, but you're bringing up an interesting thing I want to show. I think we have time for it. So we never really looked at we did look at what a simple search query looks like from the browser. But if I search for beans, I get all these back, right? Even in a simple search context, you can narrow things down by field. You can do a sort of a semi-advanced search. If you know the field names, you can do that, and it'll, it's reasonably powerful. You can say, and you can do a little bit of Boolean stuff here too. So this is basically like if you, it's what this is. This language here up here that I'm using is called just Lucene query syntax. So if you were to Google Lucene query syntax, you would basically learn how to write these queries. And so yeah, I can do that. I can even I could probably get away with, let's see where. So I'm trying to reproduce that third result without actually just saying beans. Yeah, okay. So it's in the ingredients. That's where it's coming from. Does that answer your question? Yeah. Okay. I mean, yeah, there is no natural language processing going on. Elasticsearch has a plugin API. It's not very well documented. I will say that out loud, unfortunately, but it does exist. And so you could write extensions to it. So if you want to do things, maybe pre-process things before they get indexed, that sort of thing, you can. Okay, so back to the presentation. So we're going to look at 3 requests here. They are the same 3 requests that the UI, this demo UI makes, which is indexing a document. That's what would be called when you add a new recipe. Retrieving a document, which is what you would need when you view a recipe, and then obviously searching for documents, which is what powers both the basic search and advanced search. So before we get into that, we need to understand 3 more concepts. These are more, I guess, lower level or more physical concepts. The previous 3 were more logical concepts, if you will. So we talked about indices as collections of documents. Well, an index is actually split up into multiple buckets called shards. And so when you index a document into Elasticsearch, unfortunately the word index is overloaded. So when you index a document into Elasticsearch, it's going to store it in the index you tell it to store it in, but it's going to further store it in just one shard in that index. And so it needs to decide which shard to put it in. And the way it does that is every document has an ID, either an ID that you specify at indexing time, or if you don't do that, Elasticsearch will just make one for you. And it runs that through a hashing function and then says, okay, well, the hashing function is basically index ID modulo number of shards, and it'll decide which shard to put it in that index. So that's what shards are. And they're the unit of scaling in Elasticsearch. So if you have an index with, say, 5 shards, and you have I picked a bad number. If you're an index with 6 shards and a 3-node cluster in Elasticsearch, you can be pretty much guaranteed that it's going to put 2 shards on node 0, 2 on node 1, and 2 on node 3. It's going to balance things out. Let's say you added a 4th node. It will migrate a couple of those shards over to the 4th node automatically. So that's how you scale in Elasticsearch. And you can go the other way too. And you don't have to do that. You just have to add the node, or maybe a node goes away. Typically, folks don't remove nodes. And it'll auto-balance behind the scenes for you. Speaking of nodes, a node technically is just a running Elasticsearch process. So if I have Elasticsearch downloaded on my laptop and I I run bin Elasticsearch once, and then I open a new window and run bin Elasticsearch again, now I have 2 nodes running on my laptop. In production, typically a node corresponds to a actual separate machine, whether it's a VM or a Docker container or a physical machine. In development, you tend to run multiple nodes on the same machine. A cluster then is just a collection of nodes that satisfy 2 properties. One, they should all be able to see each other. They should kind of know about each other. And they should all share the same cluster name. So that way you can have multiple clusters on the same network, essentially, without interfering with each other. It used to be that this was a lot simpler to get started with. Like it used to be the case that if we had all downloaded Elasticsearch now and we were all on the same Wi-Fi network, we all kicked it off, we would all form one cluster. It used to be that way. But that was a little too promiscuous, so we've tightened it a little more. Now it only does that for nodes on localhost. So your cluster will be different from your cluster, even though they might be named the same. Yeah. It was a trade-off between like a really nice, really simple getting started experience versus just safety. You don't want to do that, and then someone starts up a node that joins your cluster and then issues a delete from there, and then everything's gone, right? So, all right. So we're running out of time fast. So let's move on. So we're going to look, as I mentioned, we're going to look at 3 types of requests here: indexing a document, retrieving a document, and searching for documents. Let's start with indexing a document. So as I mentioned in the very beginning, Elasticsearch is a clustered system, so requests can go to any node. In this case, the request first just happens to go to node 1. Sorry, let me back up. I have a 3-node cluster here. I've shown one index in that cluster, and that index has 2 shards in it, 0 and 1. Each shard has a primary, and that's what the P0 and P1 are. And it can have a configurable number of replicas. By default, that number is 1. So in this case, it has 2 replicas. So each primary shard has 2 replicas. That's why you see a P0. That's the primary of shard 0. And then you see an R0 and an R1. I'm sorry, an R0 here and an R0 there. Sorry. And then you see a P1, and then you see a R1 here and an R1 here. So one thing, if you look closely, you'll notice is that for a given primary shard, like a P0 or a P1, you will never find its corresponding replica on the same node. That's just a safety thing, because what's the point of putting a copy of your data and its copy on the same node? Because if you lose that node, you lose both copies. So Elasticsearch will just never do that for you, which does mean that if you have a single node cluster, like in development sometimes you do, you may not have any replicas. You will only have the primary shards allocated to that node. That's OK. You can still use it. It just means you don't have any safety there. But it's development, so that tends to be OK. So now that we know the setup, we're looking at an indexing request. So the request goes into any node. In this case, it went to node 1. Node 1, first thing it has to decide is where it knows the index that this document needs to go into. It needs to now decide which shard this document, within that index, this document should go into. And to do that, it looks at the document's ID, as I explained earlier. Either it gets the ID from the client, or it generates one for you. It runs it through that hashing function, and it has decided for this particular document that we're trying to index here that it belongs in shard number 0. So next thing it's going to do is it's going to say, well, where's the primary of shard number 0? Which node does that live on? And it's found that it lives on node 3, so it sends that request to node 3 to index this document in shard 0. So document first gets indexed in the primary of shard 0, and then synchronously, it will then go and get indexed in the replicas of shard 0, wherever they may live. So the request blocks, so it's not going to return until it's indexed the document in the primary and the replicas. This is important. There used to be, I think a year ago, there used to be that Elasticsearch would let you do this replication part of it, the number 3 arrows, asynchronously, and it would just, as soon as it was written to the primary, it would return saying, I'm good. That led to corruption issues, so we just got rid of that option. Now it is synchronous. So yeah, it's a little bit of a slowdown. We're talking milliseconds here, but it's worth it because your data is not only on the primary, but it's also on the replicas. And then it just kind of goes back to the first node saying, OK, we're good, written to the primary and the replicas. And then node 1, which, by the way, you'll hear the term coordinating node. It's the node that receives the request and is handling it. The coordinating node then responds back to the client. So that's indexing a document. Retrieving is really simple. Request goes in this case, because you're retrieving a specific document, the ID is known. It said, OK, this document lives on, based on its ID, lives on shard 0. So it picks any copy of shard 0. It could have picked a primary, it could have picked a replica. It's just a read, so it doesn't matter. It does it in round-robin fashion just to sort of spread out the load. This time it went to the copy of shard 0 on node 2, retrieved the document, got back to the coordinating node, and responded to the client. Searching is where things are a little more interesting. So search request goes into, let's say, node 3. There's no ID, right? You're looking for documents. You're not trying to index a specific document or retrieve a specific document. So remember I said search request by default return 20 results. You can change that number, but let's just say we're going with the default here. So basically the client says, give me 20 results that match some search criteria, some query. So what it's going to do, what node 3 is going to do, it's going to say, well, I don't know where these results live, so I'm just going to search all the shards in this index. Well, where are the shards? Where do they live? And again, it does the round-robin thing, and it says, I'm going to pick shard 0 from node 2 and shard 1 from node 1. So it sends the same search request to both those shards. Now, each of those shards generates 20 results. So even though ultimately we only want 20 results, each of these shards are going to generate its own 20 results. And by results, at this point, all it generates is the IDs and the scores. It doesn't actually return the actual documents. It only returns the IDs and the scores in step 3 back to the coordinating node. So now node 3 has 40 results, 20 from shard 0 and 20 from shard 0 and 20 from shard 1. It has their IDs and it has their scores, right? And so what it needs to do is it needs to sort of mash them together to come up with an overall sorted list of 40 results. And because the client only wanted 20 though, it's going to discard the bottom 20. So what it ends up with is a 20 overall sorted result of 20 IDs, right? And then we get to the next phase, which is called the fetch phase, where it sends those 20 IDs back to the shards where they came from and requests the entire documents. So those come back to the coordinating node, and then it stitches them into that array that it had earlier and returns it. And so that's what's going on. So does anyone want to take a guess at why it does this search in these two phases, this query phase and a fetch phase separately? Why it doesn't just go get the entire documents at once and return them? Any guesses? Or maybe you just know? Okay. So the reason for that is, So if you're dealing with just 20 results on page 1 of your search, it's not a big deal. It could have just gone and grabbed the IDs and the documents all at once. But let's say you're dealing with 20 results on page 5 of your search, right? So think about how that would work. You still want 20 results, but they're on page 5. So to do this overall ranking, it actually needs to grab more like 100 results from each shard. It can't rank them overall unless it has the entire picture. And so returning 100 and 100, 200 results back would be expensive. So that's why it only returns the IDs and the scores. Then it will paginate into those 200 results to get to, I guess it would be results 80 through 100 after doing the overall mashing together. Discard everything before 80, everything after 100, and then in the fetch phase only get the documents for those 20 and return. So that's why it does this sort of two-phase search. And that's it. I think we just have a couple minutes for questions, but thank you very much. Any questions? Sorry.
I saw the master node. If the master node goes down, it just gets over to one of the.
Yeah, so the question is, if the master node goes down, yes, I can go back, yay. So if the master node goes down, what happens? So if you lose node 1, and you can lose node 1, by the way, in a couple different ways. It might actually die. Like there might be some kind of hardware failure on that node. Or it may be alive, it's just that there's a network partition and the rest of the cluster can't see it. So after a certain amount of time, it's going to say, well, it may be there, but I can't see it, I can't talk to it, I'm just going to call it dead. So that's how you would lose a node. So if that happens to be your master node, there is a master election algorithm built in. It will just pick another master. But that's not all, right? There's also a couple of shards on there. So losing a replica is not a huge deal. Losing the primary means you can't write to that shard anymore. So the first thing it'll do, Elasticsearch will do, once it's picked first thing it'll do is choose a new master node. The second thing it's going to do is notice that, oh my God, shard number 1 has no primary anymore. So it's going to pick one of these guys, this replica or this replica, and promote it to the primary instantly, so that now writes are available again. And by the way, all of this happens like within a second or so. It's pretty fast. And then it notices, okay, well, I have a master node for my cluster, and all my shards have a primary, so good. But I still don't have a replica for shard 0, and my replication factor is 2 in this case. So I need to have 2 replicas for each shard. So what it's going to do is on this node, because there's already a replica there for shard 0, it's going to create a replica for shard 0 by copying data over from this one. So it always tries to maintain that state of always have a master node, always have a primary for every shard, and then always have the number of replicas for every shard that it needs to, in that order. If it can't, for some reason, if it can't have a master node, then you can't do anything. You're pretty screwed at that point. But that's pretty hard to get into. Like, you would have to lose all your nodes, basically, for that to happen. If it can't have primaries, then that's also really hard to get into because you could just have all your primaries on one shard. On one node. And so, but if you don't, or for a small period of time while it's still detecting and promoting something to a primary, you won't be able to make writes to that shard. And then if you can't have replicas, that's okay. It's just your search will slow down just a little bit because it can't round robin through multiple replicas. It only has fewer things to look in. That's all. Yeah. Any other questions?
When you were indexing a document earlier, you included a type on it, even though you told us not to use types. Is that something we have to include?
Yeah, you have to. Every index has to have at least one type. All we're suggesting as a best practice is make sure it has at most one type.
Okay.
So basically exactly one type. Yeah, you do need to give it a type. It's not something it can just sort of like, as opposed to like an ID, which it can just make up. Yeah. So typically the pattern you'll see is like the index is named as the plural of something like recipes, and then the one type within it is called just recipe.
Okay.
That's typically a naming convention. That's all. I think we're out of time, but I'll stick around for some more time if anyone has questions. Thanks again.